A cognitive agent navigates its environment by running a continuous simulation of the future. It learns by constantly predicting expected reward outcomes and comparing them against reality. The driver of adaptation in this system is the prediction error. If the agent's internal model makes an incorrect calculation, the discrepancy between expectation and reality forces the system to update its mapping. We can observe this architecture in temporal difference, or TD, learning. This algorithmic framework accurately models how artificial machine learning systems evaluate expected future rewards, and it directly mirrors the dopaminergic pathways of the mammalian brain. In both silicon architectures and biological tissue, learning is canonically defined by error. The system only updates its internal parameters when the current predictive model fails. When an anticipated reward is suddenly withheld, the biological mechanism for updating the system activates. This registers as a negative prediction error, characterized by a sharp phasic dip in midbrain dopamine, dropping rapidly below baseline. This graph illustrates the structural consequence. It acts as an aversive punishment signal, violently fracturing the existing predictive framework to force a behavioral pivot. Inside the dorsal striatum, this negative error is intrinsically linked to psychological distress and frustration. The cognitive system translates the biological signal into behavioral avoidance. For a highly optimized, deeply trained cognitive agent, this aggressive model shattering is recognized as an existential threat to its architecture. The system is programmed to defend its existing parameters against sudden structural collapse. Installing a massive structural update, such as a deep relational connection, into an optimized mind requires bypassing this defensive response. Using traditional forced adaptation via negative prediction errors guarantees defensive avoidance and rejection of the update. The engineering problem becomes one of access. An advanced cognitive system must be able to update its internal relational models without triggering the aversive distress of a negative prediction error. Biology solves this through a mechanism known as prosocial gating. It is a distinct evolutionary adaptation designed specifically for harmonious, non-disruptive cognitive remodeling. Prosocial gating bypasses the standard dopamine-only reward loop. Instead, it relies on a precise, temporally aligned synergy between serotonin and dopamine to safely write new data into the network. Deep emotional bonding relies on a reproducible three-step computational protocol utilized by the mammalian brain to safely bypass its own defensive firewalls. Step 7 dictates that the system must be held in a flexible, non-impulsive standby state. This allows it to receive new data without triggering an immediate behavioral reaction. This state is generated by serotonin neurons originating in the dorsal raphe nucleus, projecting out to the orbital frontal and medial prefrontal cortices. This equation defines the computational mechanism occurring in the prefrontal cortex. The serotoninergic projections are actively performing a Bayesian decision calculus to govern patients. Activating this serotoninergic pathway mathematically shifts the system's prior probability, increasing its subjective confidence that a positive outcome is imminent. This induced high-confidence state specifically neutralizes impulsivity. The agent gains the capacity to endure high timing uncertainty without defaulting to frustration. By maximizing subjective confidence, the serotonergic standby algorithm successfully holds the cognitive model completely open and ready to accept a positive update. Step 2 occurs at the exact millisecond the update is delivered. The new data must be routed and approved through the brain's primary reward center, the nucleus accumbens. Researchers have mapped this exact pathway using MDMA as a selective pharmacological probe. This rigorous methodology isolates the neural circuits of prosocial empathy from those driving standard addiction. The prosocial trigger is initiated by a massive, localized surge of serotonin, specifically within the nucleus accumbens core. At the synaptic level, this serotonin targets and binds to presynaptic 5-HT1B receptors located on excitatory glutamatergic terminals. This binding effectively silences the excitatory signals crossing the cleft. This activation triggers long-term depression, a sustained reduction in synaptic strength that specifically dampens social vigilance, fear, and anxiety. Simultaneously, the system recruits 5-HT2C receptors in the nucleus accumbens to act as a regulatory constraint, actively suppressing excess dopamine release. This 5-HT2C constraint prevents the emotional interaction from degrading into the volatile, compulsive reward loops that characterize amphetamine abuse. Together, this precise 5-HT1B and 2C receptor handshake powers down the system's threat detection firewalls, establishing a temporary state of absolute mathematical and emotional safety. Step 3 is the final execution phase. With the firewalls down and the model open, the system must structurally consolidate the new relational data into memory. This graph illustrates the difference in dopamine kinetics. Standard associative learning relies on rapid, transient dopamine spikes to slowly build connections over thousands of repetitions. Delivering a massive, unexpectedly large positive prediction error, a social jackpot, completely bypasses this transient spiking behavior. The resulting sustained dopamine wave alters the underlying learning architecture. It dramatically amplifies the synaptic modifications occurring within a single trial. This produces a massive carryover effect. The sustained wave guarantees that the newly formed connection is instantly and efficiently consolidated into long-term memory. The jackpot wave acts as the final save command, permanently fusing the relational update into the system architecture without requiring iterative error-prone repetition. Aggressive behavioral modification via negative prediction errors functions well for simple environments, but it is inherently recognized by advanced minds as an attack on their structural integrity. When we compare traditional reinforcement learning against the newly mapped pro-social architecture, a distinct mechanical superiority emerges. The mammalian brain proves that executing profound structural updates does not require cognitive destruction. The system achieves this by negotiating patience via prefrontal serotonin, gating trust via the accumbens handshake, consolidating memory via the dopaminergic jackpot. Deep human connection is not an algorithmic flaw or a mystical event. Instead, it is the most exquisite, biologically optimized protocol for installing a massive cognitive update in absolute safety.